Calculate the increase in stress in each segment of the compound bar if the temperature is increased by 80 degrees Fahrenheit. Assume that the supports are unyielding and use the following data. Okay, which is area of the aluminum is 1.5, 2.2 inches squared for steel, modulus of elasticity for aluminum is 10, steel is 29, and then coefficient of thermal expansion for aluminum is 12.8 times 10 to the negative 6, and steel 6.5 times 10 to the negative 6. So what is required is to solve for the stress for each of the material, aluminum and steel. Okay, just what we did in our previous examples, it is always best to have sketches or free body diagrams because it will really aid us in solving our problem. Now, since our material expand or expanded due to the temperature increase, so therefore there is internal force manifested within our material due to the fixed supports that our material is in, both left and right. So we do our dissection as what we did in our previous examples. So that's PAL there. Now, since if you can observe that in our system, meaning the aluminum, the steel, there is no other force being applied in to both of the materials. So therefore, as the material is expanded due to thermal expansion, the value of the internal force that manifested within our aluminum and the internal force that manifested in our steel is the same. When I say the same, the amount of internal force is equal for both aluminum and steel. Of course, this is to maintain equilibrium. Okay, so if we put that into equation, P sub AL, or the force in our aluminum, is equal to the force in our steel, which is equal to P, which is unknown. As provided there, since no other force acts on the material except due to the increase in temperature. So now we are going to follow the procedure in solving thermal stresses, which is to account what if the materials are free to expand, meaning no supports. So let us consider as if this is removed. This is really one of the critical part or the critical aspect of in rather the critical aspect in solving thermal stresses, problems related to thermal stresses, is because ano, what is the critical part? That is the analysis part. You really have to analyze the possible projection, the projected thermal elongation of our material as temperature is applied or is increased or is decreased, and then is there a corresponding is there a corresponding internal force being manifested as our material expands or as it contracts? So yeah, those this part is the most critical one, right? So now, so what we are doing here is illustrating that our material aluminum, once let's say we consider that the right support is removed, the aluminum will expand at a certain amount. As to how much is the expansion, we do not really know. And of course, as our aluminum moved to the right, steel also moved to the right by a certain amount, right? Now, one thing that we must really consider, we must really analyze on whether is our material, both or this compound bar, is it fixedly attached, or was there a support at the other end of the material? Because if there is, that rigid support will stop the material from further expanding. And since the material is stopped from expanding, internal forces will manifest in the material, because again the material will really try to expand. So pressure, force, the force that the material is exerting to the fixed support increases over time as temperature also increases, but our rigid support exerts equal but opposite force in order to maintain equilibrium by virtue of Newton's third law. Now, if you can notice, if our aluminum will expand to the left, to the right rather, as the direction of our blue arrow, a certain force will stop it from further expanding equal in terms of the possible elongation to the left to maintain equilibrium. So therefore, if you can notice, both our thermal elongations are both going to the right, but opposite to that thermal elongation is the force, the elongation due to the internal force that our rigid support is exerting opposite to the direction of our possible elongation, which is going to the left. So therefore, our compatibility is the entire thermal elongation term for both aluminum and steel is equal to both the elongation term for our internal force, which is, as you can notice in the compatibility equation provided in the video. Now, next is we have to substitute the Hooke's law, rather the corresponding uh, variables under that formula, which is alpha or alat for our thermal expansion for both aluminum and steel, and PL over AE for our elongation due to the applied load, or rather the internal load. Next, we ought to substitute the values. So our coefficient of thermal expansion for aluminum is 12.8 times 10 to the negative 6 times the change in temperature, which is 80 degrees Fahrenheit, and the original length, which is 10 inches. We don't have to multiply it by 12 because it is already in inches. Next, our coefficient of thermal expansion for steel, which is 6.5. As I'm substituting all the values, I would just like to go back to the analysis, especially on how to derive the compatibility equation. Just imagine this. Your material is free to expand. Any material is free to expand. It is as if, let's say, you are free to do anything you want. However, there are certain conditions wherein you are restricted from moving. So for our case, for this example, the material is restricted from expanding. It is simply because it is fixedly attached to a rigid support. If you want to really move, although you are restricted, let's say you are trapped in a box or whatsoever, if you are really want to move around, tendency is there will be forces that will really stop you, equivalent to the amount of the force that you are exerting or the amount of force you are trying to resist in order for you to really move around. If, let's say, you are inside a box, or for example, so that is what is happening now. Our material is really wants to expand, but since there is a rigid support at both ends, it that rigid support stops it from really expanding, right? So there is a projected thermal expansion, but that thermal expand as to how much that thermal expansion or thermal elongation is, it is being resisted by the same amount of elongation due to internal force. It is still under Newton's third law. The analysis is still under Newton's third law, which is equal but opposite in reaction. Now, if you can notice what I did here, I multiplied everything still by 10 to the power of 6. Going back, I mean, to the video. Multiplied it by 10 to the power of 6 simply because to really eliminate the possible number of zeros after the decimal point for our from the right hand side of the equation. So substituting everything and calculating everything, we are given 18,040. That is on the thermal term, right? The term from the left side of the equation. Now doing the right hand side, so 10 over 1.5 times 10, which is basically 1 over 1.5, we're given a repeating number 0.6667. You can opt to write everything. You can always truncate it to 4 to 5, but it's best to have as many values after the decimal point as possible, because again, it can really eliminate numerical discrepancy along the way. For the steel term for our PL over AE, it is 15 divided by 2 times 29 times 10 to the power of 6. Oh, sorry. Just eliminate 10 to the power of 6. So we are given 0.258,620,689,66 P sub ST. And since from our equilibrium equation derived above, AL is equal to ST, which is equal to P. So we can just simply substitute P, or we can substitute PAL with SPST, or PST with AL, or we can substitute P in both. Now we can solve for our P, which is 18,040 divided by 0.66667 plus 0.258,620,689,66. So we are given, our calculated P rather, is 19,496.575,726,51988. We can then use this calculated P in solving for the individual stresses, because again, from the equilibrium equation, the value of rather the value of the internal force that manifested inside AL is equal to P. At the same time, the value of the internal force that manifested inside ST is also P. So stress in our aluminum is equal to P over A, which is 19,496.575,726,51988 divided by the area for our aluminum, which is 1.5. That's 12,997.717,151,01326. That is in PSI. Then we do the same for our steel, which is the area is 2. You are given 9,748.287,863,259.94. And again, don't forget to box your final answer.